Hello everyone, so today we're going to talk about cross products, and this is really a complementary video to our video on dot products, where here we complete the picture for vector products. So let's dive right in. So we defined two vectors, vector A and vector B. Vector A is AX, AY, AZ, B is BX, BY, BZ, Z or Z, whatever you prefer, and we can form a plane using those two vectors, and we align the iPad with that plane. So we can draw this diagram over here. So we have vector A here, vector B, which is here, and I also drew in the perpendicular component of A with respect to B. So WRT is with respect to. And this is A sine theta using basic trigonometry because the angle between A and B is theta. Well, then we define the cross product as A cross B here is equal to the magnitude of A times the magnitude of B times sine of theta times this unit vector AB, unit vector E in the direction of A cross B. Well, okay, let's unpack this a little. Well, this is the magnitude, and this is the direction, right? And then the magnitude can be written as A sine theta B. And what is A sine theta B? Well, if you look at this diagram here, it's the area, right? And that's exactly what I draw here. So A sine theta times B gives the area, which is shaded here, of this parallelogram formed by vectors A and B, with this being A, this being B. Right? However, it has a direction, and that direction is shown here. So the cross product is really some form of vector area, and to some of you this might be surprising. Why am I calling an area a vector? Well, the vector points perpendicular to the area, and the direction is decided using a convention which is known as the right-hand rule. And if you've taken any exams in physics or maths or in engineering, you will know that the exam room looks funny with all sorts of hand gestures which look a bit like this. Well, this is my anatomically correct drawing of a hand with the thumb pointing in the direction of A cross B here, the index finger pointing in the direction of A, the middle finger pointing in the direction of B. There we go. And immediately from this, what you can tell is that these two, A and B, are found in a plane, and A cross B is perpendicular to that plane. So we can say that A cross B is perpendicular to A and is perpendicular to B. And for your benefit, I also included a more correct drawing of a hand with the same directions. So again, the thumb points in the direction of A cross B, index in the direction of A, and middle finger in the direction of B. And you should practice that a few times in order to get the hang of it. So, okay, so that's the definition here. And we know how to calculate the magnitude because it's an area, and the direction is given by these two drawings, essentially. Sorry. So immediately looking at this definition, we can find three properties. So the first one is quite simple. Well, if A is parallel to B, then A cross B must be 0. And this is the 0 vector, just for correctness. But it's really, you should treat it as exactly the same thing. So why is that? Well, it's because sine theta is 0 if theta is 0. The second property is that if A is perpendicular to B, well, A cross B is just the magnitude of A times the magnitude of B times some unit vector. And that's equivalent to finding the area of a rectangle A, B, and finding that area of this rectangle here. So this is perpendicular, and then the magnitude gives the area shaded. And remember, what is the direction? Well, A cross B, so the direction will point out of the page, and I'll show it with this arrow clockwise. Those of you who know the right hand screw rule will know what I mean, and this is A cross B, which essentially points out of a plane towards you, so out of your computer screen pointing towards you. And from the right hand rule, we can immediately see that A cross B will be minus B cross A, so here. And why is that? Well, if I draw the same rectangle as I just drew, with B and A, this is perpendicular, well, the area stays the same as before, so this is still the area, except the vector is reversed because now we're going in that direction. So B cross A. And so if you're looking at a computer screen, the vector would point into your computer screen. So the arrowhead would point towards your computer screen. However, some of you by this point will be a bit confused because the way that cross products are generally introduced is using a 3x3 determinant, as shown here. So in a sense, it looks like a 3x3 determinant of a matrix. There you go. And using that definition, we can come up with this result. So A cross B is AYBZ minus AZBYEX minus AXBZ minus AZBXEY, and the final line here for EZ. The question is now, can we derive this, which is the algebraic definition of the cross product? Can we derive this from our geometric definition? How are they related? Geometric definition. Well, to see really how they are related, you would have to wait for the course on linear algebra, which is quite nice when you look at determinants of matrices. But we can prove this formula using some simple maths, and we do that next. But first, let's have a look at what happens when we take the cross products between unit vectors. Well, this is our run-of-the-mill coordinate axes, EX, EY, EZ, and from the definition, from the geometric definition, it's pretty clear that EX cross EY will give EZ, EY cross EZ will give EX, and EZ cross EX will give EY. Why? Because they all have a magnitude of 1, so the magnitude will be 1, and the direction will be perpendicular to the two vectors here. So in a sense, you can form this square of side 1, this is area of 1 again, so let me draw it in red, 1, and the vector points in this direction, EZ. And then using property 3, which is A cross B gives minus B cross A, we can see that, for example, EY crossed with EX would give minus EZ. Right? And a useful way to remember this, I find, is to use this circle here. So EX with an arrow goes to EY, with an arrow goes to EZ. And basically, if you take any two vectors, so let's say EZ crossed with EX, you get EY. So if you go in the direction of the arrows, you always end up with a positive result. And that's the useful way I found to remember it. Now, using the above, we can write A cross B as ax ex plus ay ey plus az ez crossed with bx ex plus by ey plus bz ez. And now what we can do is distribute over the brackets to obtain, well, if you look at the first term, let me change color. So ax ex crossed with bx ex, you obtain this term right here, which is ax bx ex crossed with ex. The second term, ay ey crossed with by ey, so this term right here, sorry for the mess, you get this term, ay by ey crossed ey. And every term, if you distribute all the terms over the brackets, you will end up with this massive formula. And this looks a bit like a matrix, right? You have 3 terms on each row. Now, using the properties that we just mentioned, we can cross out some terms. So ex cross ex will be 0 because ex is parallel to ex, they are both the same. Again, this is 0, ey cross ey, ez cross ez will be 0. And you can already see that some terms will be positive while some terms will be negative, as given by this rule here. And if you group the terms with similar ex, ey, and ez, you will get exactly the same formula. So exactly the same formula. So you might say, well, we haven't used the geometric definition at all, and you just distributed like a normal product, but hang on a minute. To be allowed to distribute over the brackets as we've done here, we must ensure that the cross product is linear. And what I mean by this is we need to prove that u plus v crossed with w is the same as u cross w plus v cross w. Because we don't know beforehand if our definition of cross products agrees with linearity. And by definition of cross products, I mean the geometric definition. So we don't know whether we are allowed to distribute over the brackets. So how do we prove this? How do we prove u plus v cross w equals u cross w plus v cross w using only geometry? Well, this is kind of similar to the proof for dot products. And here I will draw in orange. There we go. And I drew a vector u in blue, a vector v in red, and this vector in green is u plus v. And the lines I drew are the projections. So this line is the projection of u onto w, but the perpendicular component of u onto w. So it's not exactly the projection, I should say it's the perpendicular component of u with respect to w. And the same here, this is the perpendicular component of u plus v, oops, sorry, let me erase this and to be cleaner, u plus v onto w. And similar for the red line, which is here, the red line here. So now, we know, so first things first, we know that u plus v, oops, so u plus v, v and U form a closed triangle. And that is just from basic vectors, basic vector addition. And you can clearly see it from the diagram here, so this triangle right here. So because we form a closed triangle, their projections also form a closed triangle, and this is shown by this closed triangle over here. So this is the closed triangle of projections. But now you have to imagine what the cross product does to this projection. Well, I keep saying projection, but it's perpendicular component. So here I write that u, v, and u plus v form a closed triangle, so their projections must also form a closed triangle. So the cross product, remember u cross w equals u w sine theta, and then it has some direction eu cross w. Well, essentially what we're doing is we rescale the projection by w, so the projection is u sine theta, and we rescale by w. And then this is essentially rotating the magnitude of the area that we obtain, and we rotate it. So essentially what we will get is we will get three vectors, each perpendicular to this line of this perpendicular component. So this one has a vector which will point in some direction which looks like this. The red one will have a vector which points this way, and the green one will have a vector which points kind of in the middle of them too. So let me redraw these because these are not great. So this vector points a bit like this. This one points a bit more upwards, and basically we get three vectors. And those three vectors have to form a closed triangle themselves because the perpendicular components of u, v, and u plus v form the closed triangle themselves, and we are rescaling every side by w and rotating such that they are at 90 degrees. So we will obtain a closed triangle. So for vectors u cross w, v cross w, and u plus v cross w form a closed triangle. So the closed triangle will still exist because rescaling factor is the same, so the rescaling factor is w, and we rotate by 90 degrees. I should not say the same angle. This is 90 degrees. Let me erase this. There we go, my 90 degrees. Therefore, we've proved it. So indeed, u plus v cross w must be u cross w plus v cross w. And I know this is a bit hard to understand at the start, especially because I've got a bit of a poor diagram going on here, but if you really think about it, and you should get it at some point. If not, please leave a comment and I might be able to address it a bit better. So the derivation is indeed correct, and so we can see that the algebraic definition agrees with the geometric definition. Okay, so now let's move on to some applications. Well, what are the applications of the cross product? So, and I'm sure there are plenty more than I will be able to list here, but these are the ones I've used a lot at uni. So first is the Biot-Savart law. And most of you will have encountered some version of the Biot-Savart law if you've taken some elementary magnetostatic course. And I'm here talking about the magnetic field B being equal to mu over 4 pi the integral of the current density evaluated at some point x prime, and I'll define those in a diagram in a minute, crossed with x minus x prime divided by x minus x prime to the cube dv prime, and you integrate over all of space. So you've encountered this formula in high school, but in a bit of a simplified form. And to better understand, let me draw some axes. So x, y, z, and let's see, so this is our origin. Here you have a rectangle, so which is say a current line, so which goes like this, j, and this is the vector x prime. Let me change colors now, and let me change the thickness of the line. There we go. And let's say you want to compute the magnetic field at some point given by this vector x. Right, so then the vector between the two is shown here as x minus x prime. And essentially, what you need to do to compute the magnetic field at this point, B, is, well, I'll call it dB because it's due to this small element of current here. So dB would be given by j at x prime crossed with this vector, and then you divide by the magnitude of the vector to the cube, which I drew here. So I'm not going to write the whole formula again, but if you do the integral, you get this. And the Biot-Savart law turns out to be way more useful than just in magnetostatics. In particular, it's very useful to calculate the velocity field from, say, a tornado. Okay. So that was just to show you what the cross products are used for. You don't really need to know the Biot-Savart law if you haven't met it yet. A second application would be to find a vector which is perpendicular to two other vectors. So let's see. And I should probably have talked about this one first. Well, if we have a vector A and we have a vector B, and we want to find a vector perpendicular to A and B, we want a vector perpendicular to A and B, let's call it, say, C, then you can immediately find one by using A cross B. Right, so A cross B for any vector A, and say you have another vector B, then A cross B would be perpendicular and would be C. So here C would point out of the screen, so C, and it would point towards you, outside of your towards you, pointing out from your computer screen. Okay, and a third application, and I've used this a lot at uni, is plotting, say, streamlines for a velocity field. It might be electric field lines, it can be current lines, it can be magnetic field lines. And how do you do this? Well, you know that those geometric objects, so streamlines, electric field lines, or current lines, they are parallel to the velocity u, e, and j respectively, right? So what I mean is the velocity vector u is parallel to streamlines, the electric field vector E is parallel to electric field lines, and J is parallel to current lines at each point. So that's the definition of streamlines, electric field lines, and current lines. Well, how do we find them? Well, we have many ways of doing this, but one way which I found particularly useful is, say we consider streamlines. Well, U is parallel to DL, where DL is part of a streamline. So we have a streamline here, and at each point the velocity vector would be parallel to it. There we go. So how do you do this? Well, you can immediately say that U crossed with DL gives 0, and if in 2 dimensions, then you can represent DL as dx ex plus dy ey, and then U cross DL will be, well, let's use what we've just learned, crossed with dx ex plus dy ey. And what do we get? Well, we get ux dy, sorry about this, minus uy dx, and this will point in the ez direction. How do I get this? Well, it's ux ex times or crossed with dx ex, so that's 0. We get ux ex crossed with dy ey, which gives this term times ez. Then we get uy ey times dx ex, which gives this term here, uy dx, but minus ez, because ey cross ex gives minus ez. And then the last term, uy ey crossed with dy ey, gives 0, because they are parallel. So now this has to be 0, because, you guessed it, U is parallel to DL, and this is by definition. Sorry, this is parallel to DL. So therefore, what you end up with is ux dy minus uy dx must be 0. And therefore, you get dy dx must be equal to uy by ux, and this is an ordinary differential equation, an ODE, ordinary differential equation, and then you can solve this to get y as a function of x, and then you can draw your streamlines. So that's it for today. Thanks